The division algorithm is one of the most important results that we'll have in this first chapter, and it's very simple but very powerful. So we know from elementary school that it's not always the case that if you pick two random integers that one will divide the other. Okay, we don't know. In general, that's not going to be true. But we can attempt to divide those integers. That's certainly true. And when we attempt to divide them as much as possible, there is usually a leftover piece. That leftover piece is the remainder, and then there's sort of the number of times that our term went into the other one of the integers went into the other one. That's called the quotient. And the division algorithm is a formalization of that. So suppose we have two natural numbers, so positive integers. The division algorithm tells us that there exist integers q and r, q for quotient, r for remainder, such that b will go into a q times, but there might be a leftover piece. And to ensure we've divided b into a the maximum number of times possible, that leftover piece should be less than b. Because if it was bigger than b or equal to b, we could divide another b into a. So our r is special. Our r is somehow the smallest possible remainders of all possible remainders. And we know, for example, that there could be lots of q's and r's that work. So here's an example. Here's a couple examples here. 5 we can write as 3 times 2 minus 1. We can also write it as 3 times 1 plus 2. We can also write it as 3 times 0 plus 5. So there's lots of different ways of writing it. But in this case, only one of these of the different r's we have, negative 1, 2, and 5, only one of them is in between 0 and less, is bigger than or equal to 0 and less than 3. It's this guy, it's this 2. Only one works. And this q is also unique. There's only one quotient, it's 1. So not only does there exist integers, but there exist unique integers such that this happens. And this uniqueness is very important, as we'll see. So take a moment, and again, we'll prove this in class, but try to work it out on your own. And in class, we encountered these specific sets that looked vaguely like a is bq plus r, and we used the well-ordering axiom to do something, namely find a least r. So I want you to go back and look at those examples and try to figure out what set you might use the well-ordering axiom on.